Hi everyone. In today's session, we are going to discuss about batch normalization and how it benefits your network architecture. So let's begin. The first slide that you see here talks about a generic idea of batch normalization, like what exactly it does. So as you can understand from the word normalization, it has to normalize something. So what it normalizes? If you see the architecture as shown on your screen, it is trying to normalize the Z values in this network. For example, you can see a layer 2, which is a hidden layer in this network. So batch normalization can be applied to this hidden layer, and it will normalize the values Z21 and Z22, which are the two Z values for the two nodes available in the hidden layer. That's the basic idea of what it normalizes. The same thing can also be applied to the activations of layer 2. That means that we can apply batch normalizations either to the Z values or to the activated values. But general practices apply batch normalization to the Z values of the network layer. Now, if you see on the second slide, in this slide, it gives you an idea about what exactly is happening internally when you apply batch normalization. So make an assumption that there is a network which contains a hidden layer. That hidden layer has 5 nodes. And the Z values that you see on the right hand side, Z21, Z22, Z23, 24, and 25, are the 5 Z values for the second layer, second hidden layer of this network, containing 5 different nodes with 5 different values. Now, what exactly would batch normalization do when we are applying it to the Z values of the second layer during training time? So you have these 5 Z values. Now, let's assume you have a batch containing so and so, or let's say 10 samples or 10 data points, and you will have multiple batches like this. So in one batch, in these 10 samples, you would get 5 into 10 values of Z in the layer 2 of the network. That's the same thing that you can see here in the computation. Z21, Z22, Z23. The first row in this computation of Z bar belongs to sample 1. The second row belongs to sample 2. And the last layer would belong to sample 10. So in order to normalize the Z values, we need to get all the values at the hidden layer number 2 for Z values. And then we do a find out the mean for Z values here, which is given here in the computation. And using this mean value, we also calculate the normalized Z value, which is given, the computation formula is given on the top. Now we have normalized Z value. So what is the next step? The next step in computing batch normalization or in doing batch normalization is to create something called as Z tilde. Z tilde is the lower computation that you see. What Z tilde does, it multiplies Z normalized values with a factor gamma and then adds the output to a shift operator beta. Right? Now, an important thing to note here is we talked about normalization being done for Z values. So it is called as normalization, but actually we are doing standardization. So we should know the difference between standardization and normalization. Normalization will limit your values between 0 and 1, but standardization will make the value of mean of your distribution as 0 and your standard deviation of the distribution will be 1. That means your most of the values will be between -1 to 1, but you'll still have values beyond this range. So standard normal behavior is what we are doing here to the Z values, even though the naming says normalizing, but internally it is standard normalization that we are doing. Now, coming back to Z tilde, you see the two values gamma, G, and beta. Once we have done this computation of gamma and beta with the Z normalized, we get Z tilde values in front of all the basic Z values that we had earlier, right? So now you have done or applied batch normalization to your Z values in the second hidden layer. That means you have converted the Z values to Z tilde values. How you converted it? You converted it by normalizing the Z values and then by multiplying it with the gamma, and then by adding a shift operator to it, which is called as beta. Now we need to understand what is shift and what is scale. So in the formula of z tilde, we are multiplying normalized z value with gamma. That means we are scaling it. And when we are adding a value beta, that means we are shifting the distribution of data. So as you can see in this diagram, on the left-hand side, you have a standard normal distribution. When we scale it up, the values are actually trying to spread around, right? So you can see here on the left-hand side and on the right-hand side, the top chart, the values are getting further apart when we do a scaling of the values. But when we do a shifting, that's the bottom chart that you see. In this diagram, the overall distribution has started to shift. In the base distribution, you had 0 as the mean, but in the shifted distribution, you are having 1 as the mean. That is the difference between shift and scale. Scale would widen the data distribution, and shift would move the data distribution as to a different point. Now, question is, how do we update the values of gamma and beta? So gamma and beta are generic parameters, just like any other parameter of the network, right? So that means this should be updated in the exact same way as other parameters are getting updated. The other parameters are weights of the network, and weights of the network are getting updated through gradient descent, let's assume. So that means beta and gamma should also get updated through gradient descent, right? Now, in the initial phase, or in this first step, we always initialize weights with some random values. Similar way, we initialize gamma and beta also, but not with random values. Gamma is initialized with 1 and beta is initialized as 0 with most of the standard libraries used in deep learning. Now, if we remember the process of updation of weights in the backward propagation, the same is carried out here. So if you see here, the error gradients with respect to the beta are calculated for each of the samples, right? So in this row, you have sample number 1. You have 5 beta values for 5 nodes available in the second hidden layer of the network. So you would have error gradient with respect to beta 1, error gradient with respect to beta 2, and so on till error gradient with respect to beta number 5. And this complete row containing 5 values will be for sample 1. Same way, you'll get 5 different values or 5 different values in a vector for all the 10 samples. Once you have got the error gradients with respect to beta of all the samples, you would do the average. That gives us the error gradient with respect to beta average value. Once you are done with this, you will compute the new beta value based on the gradient descent formula, which is beta new is equal to beta old minus learning rate into error gradient with respect to beta average. So this is a generic way on how to update the values of beta and gamma when it comes to training of a network containing batch normalization in one of the layers. Now, the next thing is, we talked about the training time, but how about the test time? We face one challenge during the test time or the validation time is that how do we normalize the Z values? During the training time, we are dealing with a batch, and a batch would have many samples. So then normalization would make sense. But during validation time, we are passing one sample at a time. And when we pass one sample at a time, we don't have anything to normalize the data, right? You have 5 Z values, you can't really do much with it. So what we do is, in order to compute the values of Z bar or Z mean for test validation time, what we do to compute this, we actually reach out to the train set. During the training time, the values of mean of Z in the second layer of the network and the standard deviation of Z values in the second layer of the network in the last iteration of the train time. So whatever these values were there in the last iteration of the train time, we get those values and plug them in during the test time. So that is a simple approach. The other approach is, if you do 10 iterations in the train time, during each iteration, you save the value of the Z mean and Z standard deviation in an array. So by the end of 10 iterations, you would have 10 values of Z mean and 10 values of Z standard deviation. you do a weighted average on top of these mean and standard deviation values to find one common value of z mean and z standard deviation, and use that mean and standard deviation to compute the values of normalized z during the test time or the validation time. That is what is written in this step here. Now, what would happen if we don't have beta and gamma? Just think about a scenario where we don't have it, right? But we're still normalizing the values of z, right? Batch normalization is about two steps. One is normalizing the values of b and then doing a multiplication and an addition with beta and gamma and so on. So out of these two steps, we are at least doing one step, which is normalization. So once we do normalization, the mean of the entire data set or the entire z values would shift to 0. Assume that you are using a sigmoid function as an activation function during the batch normalization layer. So that means if you apply batch normalization to the second layer and you don't use beta and gamma, but the activation of the second layer uses sigmoid, in that case, you could see this kind of behavior. All of your data is just within or just below the sigmoid function actually. So that means even if sigmoid is applied or doesn't apply, it does not really matter to this data. Nothing is getting clipped, nothing is getting changed at all. So the sigmoid is almost same as not applying anything, right? So that's the reason we use beta and gamma. We can use beta and gamma, do some sort of a distribution, and then do some sort of a shift with which this data, which is in the lower part of sigmoid, will shift either here or will distribute wider, right? So that there is some use of sigmoid function that we see in the network. That's the use of beta and gamma, why it is used. The other reason is generally when we are normalizing the z values, we are assuming that z values of the second layer of the network is generally having a normalized distribution, but it may not be always the case that z values have standard normal distribution, although we are making it converted into a standard normal distribution. So to account for those changes or to account for those cases when the values of z in the second layer are not standard normal, but we are forcibly making it standard normal, they have provided a value of beta and gamma to accommodate for those cases. Right? Next, we also need to understand few of the things that batch normalization does to the network that are really making the network do wonders. One of the major things is the speed of the training. So now with batch normalization, the speed of the training is increased. The reason is you don't have those wide variety of z values flowing into the network, right? When you have z values really high and really low flowing into the network, in that case, the time required to achieve the global minima will be very high. But when you try to keep z values within a range or within a controlled fashion, they may not be completely standard normalized because we are using beta and gamma, but still they will be in a range or a limit. They will not be like really widely varying for every iteration, right? So batch normalization reduces the distribution or reduces the variety that could have been there in Z, and this in turn increases the increases the speed of the training and reduces the time taken to achieve the global minimum. And another important thing that we need to see is that it can also be applied to the input layer of the network, right? So batch normalization, the way it is applied to the hidden layer, same way it can be applied to the input layer. It's just that in the input layer, it will end up normalizing the feature values and not the z values. Another important thing to note is when you are using batch normalization, then you don't need a use bias flag in the network layer. So let's try to understand this by this formula. So your z value is generally defined based on w, x, and b, right? Or w, a, and b. W, x, and b when you are talking about the first layer, w, a plus b when you are talking about the later layers. In both of these cases, if we apply normalization to z values or to batch normalization, that means we are shifting the distribution of z values to mean of 0, right? So after we have computed z values, we are making sure that the mean again comes back to 0. But in computation of z values, we are adding a factor or a shift variable called as b or bias. Then what is the use of this b? Use of the b is to shift the distribution, right? So you're shifting the distribution somewhere else, and by normalizing the data, you are getting it back to zero. So that means bias has no value here when you're using Bayes normalization. That's why bias flag is always set to false in these cases. Anyways, the data distribution shift is handled while doing Bayes normalization by the things that we are adding in Bayes normalization, which is beta and gamma, right? If we scroll down to the previous sections of the computation, you can see beta is the parameter that is responsible for shift. So any shift which is required to be done by bias, beta will anyways take care of it. So now coming back to the last page of this PPT. So Bayes normalization also helps with respect to preventing vanishing and exploding gradients. Now we will touch upon vanishing and exploding gradients later on also, but one of the key reasons that vanishing and exploding gradients do happen is because of the weight. The weights in the network are really high or really low, thereby exploding or vanishing the gradients. But Bayes normalization, what it does, it actually normalizes your z value. And z values are made up of W, X, and B. W is the weight value, right? So thereby it limits the variations in W, because ultimately whatever value W has, when you compute Z, you again normalize it back to the mean of zero. Right? So that way it is preventing the probability of exploding the gradients or vanishing the gradients. Then an important point to note is batch normalization also helps in regularization. So regularization means generalization of the network, making the network less sophisticated. How does it happen? This happens because batch normalization adds a bit of noise to the network. How does it add noise to the network? Batch normalization is unintentionally adding some noise to the network because it works on many batches. And for one batch, let's say you have only 10 samples, but in overall data, you have 100 samples. So when you are doing batch normalization, you are computing the mean and standard deviation of only these 10 samples, or with respect to the z values which are there because of these 10 samples. When you go to batch 2, you will have the z values which will correspond to the next 10 samples. So that means these z values which are there for the samples, whatever mean you get out of the z values in the first batch will obviously be different from the mean value of z that you get out of batch number 2, right? So that means your sample mean is not same as population mean. You are unintentionally introducing some sort of a noise in the network by giving a mean value or a standard deviation value of z which is not accurate. Right? So this is how you introduce unintentionally some noise in the network, making it more generalized, more regularized. So this brings us to end of this presentation. In case you have any questions, feel free to leave a comment there. Thank you so much. Have a great day. Bye.